Welcome to Sleepless Philosophers, where deep ideas meet restful nights. If you enjoy these journeys through philosophy, please like and subscribe and turn on notifications for daily uploads. To support the channel, consider leaving a super thanks. Any amount helps us continue creating content. You can also become a member to request video topics. We're not monetized, so your support truly makes the difference. Now let the philosophy begin. Fichte's paradox of knowability. There is an appealing idea in philosophy, a principle that seems to capture something important about truth and knowledge, and this is the knowability principle, which states that all truths are knowable, that for any true proposition, there is at least a possible situation in which someone knows that proposition, and this principle seems modest, even Platonic in spirit, suggesting that truth and knowledge are intimately connected, that reality is not fundamentally hidden or inaccessible, that the universe is intelligible in principle, even if not all truths are actually known by anyone at any given time. The principle distinguishes between what is known and what is knowable, acknowledging that many truths remain unknown, perhaps because no one has investigated them, or because the evidence is lost, or because the relevant questions have not yet been asked, but insisting that these unknown truths could be known, that there is no barrier in principle preventing them from being discovered. And this seems like a reasonable position, neither too strong like the claim that all truths are actually known, which is obviously false, nor too weak like the claim that some truths are unknowable, which seems to concede too much to skepticism and to suggest that reality contains secrets that are forever beyond our reach. But in 1963, Friedrich Fichte proved a shocking result, a theorem showing that if the knowability principle is true, then all truths are actually known, that the modest principle collapses into the absurdly strong claim it was meant to avoid. And this result, known as Fichte's paradox or the knowability paradox, has profound implications for epistemology, the philosophy of language, and debates about realism and anti-realism, and it forces philosophers to choose between giving up the knowability principle, accepting the absurd conclusion that all truths are known, or finding some way to reformulate the principle to avoid the paradox. The proof is elegant and surprisingly simple. Proceeding by reductio ad absurdum, suppose there is a truth that is unknown, call it P, and suppose also that no one knows that P is an unknown truth. That is, no one knows the conjunction P, and P is not known. And now apply the knowability principle, which says that this conjunction, being true, must be knowable, must be such that someone could know it. But here a contradiction emerges, because to know a conjunction, one must know both conjuncts. So to know P and P is not known, one must know P and also know that P is not known. But if one knows P, then P is known, which contradicts the second conjunct that P is not known, and so the conjunction P and P is not known cannot be known. It is an unknowable truth, and this contradicts the knowability principle, and therefore the assumption that there is an unknown truth must be false, and so all truths must be known. The paradox depends on the assumption that knowledge distributes over conjunction, that if you know P and Q, then you know P and you know Q, which seems uncontroversial, and on the assumption that knowledge is factive, that if you know P, then P is true, which is a standard requirement in epistemology, and so the paradox cannot be easily dismissed as relying on dubious principles. It seems to follow from our ordinary understanding of knowledge and knowability, and yet the conclusion is unacceptable. The claim that all truths are actually known is empirically false. There are obviously truths about the distant past, about the far reaches of the universe, about the inner workings of consciousness that no one knows. And so something must give, either the knowability principle or the reasoning that derives the paradox from it. One response is to reject the knowability principle, to accept that there are unknowable truths, truths that could never be known by anyone under any circumstances. And this is the position of semantic realists who argue that truth is independent of our capacity to recognize it, that reality outstrips our epistemic abilities, that the world contains facts that are forever beyond our ken. And for realists, the knowability paradox is not a disaster, but a vindication, a proof that the anti-realist commitment to knowability is untenable, that we must accept a more robust conception of truth as radically independent of knowledge. Another response, favoured by anti-realists and verificationists, is to reformulate the knowability principle to avoid the paradox while preserving the intuition that truth and knowability are connected, and various reformulations have been proposed. Some restrict knowability to propositions that do not involve knowledge ascriptions. Avoiding the problematic, self-referential structure of P and P is not known. Others distinguish between individual and collective knowability, arguing that all truths are knowable by the epistemic community as a whole, even if not by any single individual, and still others embrace a temporal or modal reformulation, claiming that all truths could have been known at some time or in some possible world, rather than claiming that all truths are actually knowable in all circumstances. Some philosophers argue that the paradox reveals a tension in the concept of knowability itself, that knowability is not a simple modal notion, but involves complex interactions between truth, knowledge, and the conditions under which knowledge is possible, and that our intuitions about these interactions are unreliable, pulled in different directions by competing commitments, and so the paradox exposes an instability in our conceptual scheme, rather than refuting any particular philosophical position. The paradox also connects to debates about the nature of propositions and the objects of knowledge. Because the problematic conjunction P and P is not known seems strange, it is a proposition about itself in a way, a proposition whose truth depends on whether it is known, and this self-referential or quasi-self-referential structure is reminiscent of the liar paradox and other semantic paradoxes, and some responses to Fitch's paradox draw on strategies developed for dealing with those paradoxes, such as hierarchies of languages, restrictions on self-reference, or non-classical logics that reject certain principles like the law of excluded middle. The paradox has implications for constructivism in mathematics and logic, because constructivists typically endorse some version of the knowability principle, identifying truth with provability or constructibility, and Fitch's paradox threatens this identification, suggesting that even constructivists must either accept that all mathematical truths are already proved, which is absurd, or abandon the simple identification of truth with provability and develop a more nuanced account of the relationship between the two. The knowability principle, innocent as it seemed, turns out to be a Trojan horse, a seemingly modest claim that conceals a radical commitment, and Fitch's paradox forces philosophers to confront the costs of various epistemological positions, to choose between realism with its unknowable truths and anti-realism with its need to reformulate or restrict the knowability principle, and the paradox remains a central puzzle in contemporary epistemology, a test case for theories of truth and knowledge, a proof that demonstrates with crystalline clarity that even the most intuitive principles can lead to absurdity when their logical consequences are rigorously traced. And it stands as a reminder that philosophy is not merely a matter of articulating and defending intuitions, but of following arguments wherever they lead, even when they lead to conclusions that undermine the very intuitions that motivated them. And the unknown truth, the proposition that is true but not known, sits at the center of the paradox, both knowable and unknowable, possible and impossible, a conceptual anomaly that refuses to be tamed by logic or softened by reformulation. And the paradox endures, a monument to the power of formal reasoning, to reveal deep tensions in our most basic concepts, tensions that no amount of philosophical maneuvering has yet managed to resolve in a way that satisfies all intuitions and preserves all principles. And so the debate continues, philosophers proposing new solutions, new restrictions, new interpretations, and the paradox persists, waiting to trap the unwary, to challenge the confident, to remind us that even truth and knowledge, the twin pillars of epistemology, are stranger and more problematic than they first appear. Grandi's series, when adding numbers, forever gives multiple answers. A simple mathematical series begins with 1 minus 1 plus 1 minus 1 plus 1 minus 1, continuing forever without end, alternating between adding 1 and subtracting 1. And the question emerges, what does this infinite sum equal? What value does it approach as more and more terms are added? And the paradox is that different methods of calculation give different answers, each seemingly valid, each following mathematical rules, yet reaching contradictory conclusions. And this is Grandi's series, named after the Italian mathematician Guido Grandi, who studied it in the early 18th century. And the paradox reveals fundamental questions about what it means to sum an infinite sequence, about whether all infinite series have definite values, and about the limits of algebraic manipulation when dealing with infinity. Consider the series visually. Imagine a number line where you start at 0, then move 1 unit to the right to reach 1, then move 1 unit to the left back to 0, then 1 unit right to 1 again, then 1 unit left to 0, and this pattern continues forever, oscillating between 0 and 1, never settling down, never approaching a limit in the traditional sense. And so, from this perspective, the series does not converge, does not have a sum. The partial sums bounce between 0 and 1 eternally and never stabilize. But now consider a different approach. Group the terms in pairs, taking 1 minus 1 as the first pair, which equals 0, then 1 minus 1 as the second pair, also 0, and so on. And the series becomes 0 plus 0 plus 0, continuing forever. And the sum of infinitely many zeros is 0. And so by this grouping method, the series equals 0. And this seems like a valid manipulation. Grouping terms is a standard algebraic operation, and yet it produces a definite answer where the oscillating view produced no answer. Now consider another grouping. Start by leaving the first one alone, then group all subsequent pairs, so the series becomes 1 plus the quantity negative 1 plus 1, then the quantity negative 1 plus 1, and so on, and each grouped pair equals 0. So the series becomes 1 plus 0 plus 0 plus 0, continuing forever. And this equals 1, and so by this different grouping, the series equals 1 instead of 0. And both groupings seem legitimate. Both use standard algebraic rules, yet they produce different answers, 0 and 1. And this is the heart of Grandi's paradox, that the series is sensitive to how it is manipulated, that rearranging or regrouping terms changes the result. And this suggests that the series does not have a well-defined sum in the ordinary sense. Mathematicians have developed sophisticated tools to handle divergent series, like Grandi's, and one approach is Cesaro summation, which assigns values to series by averaging the partial sums. And for Grandi's series, the partial sums are 1, 0, 1, 0, 1, 0, continuing to alternate, and the average of the first n partial sums approaches 1/2 as n grows large, because roughly half the partial sums are 1 and half are 0. And so by Cesaro summation, Grandi's series equals 1/2, and this method produces yet another answer, neither 0 nor 1, but the midpoint between them. And this answer has a certain aesthetic appeal. It represents the average behaviour of the series, the value around which it oscillates, and it can be justified by analogy to functions. If you consider the geometric series 1 minus x plus x squared minus x cubed and so on, which converges to 1 over 1 plus x for absolute value of x less than 1, and you plug in x equals 1, you get 1 over 2. And so in some extended sense, Grandi's series can be said to equal 1/2. The paradox reveals that divergent series do not have sums in the way convergent series do, that assigning values to them requires making choices about what summation method to use, and different methods give different results. and there is no single correct answer, but rather a family of possible values, depending on the context and the techniques employed. And this multiplicity is not a flaw in mathematics, but a feature, a recognition that infinite sums are more subtle than finite sums, that operations that work for finite cases can break down or become ambiguous when extended to infinity. Grandi's series appears in physics and engineering, in Fourier analysis, where oscillating sums arise naturally, in quantum field theory, where divergent series are regularized using techniques similar to Cesaro summation, and in signal processing, where alternating patterns must be analyzed. And in these applications, the choice of summation method is guided by physical considerations, by what gives useful predictions, by what aligns. With experimental results, and the paradox becomes less troubling, less a contradiction, and more a reminder that mathematical tools must be adapted to fit the problem, that formal manipulation must be tempered with judgment about what makes sense in context. The series also appears in philosophical discussions about infinity, about whether infinite processes can be completed, about whether the phrase, sum of infinitely many terms, has a determinate meaning or depends on conventions and choices. And Grandi's series suggests the latter, that infinity introduces ambiguities that finite mathematics avoids, that extending concepts from finite to infinite is not automatic but requires care, requires new definitions, requires acceptance, that some questions have multiple answers or no answer at all depending on how they are framed. Imagine watching someone walk back and forth on a path, taking one step forward, then one step back, then one step forward, then one step back, forever without stopping, and you're asked where they end up, and the answer is that they do not end up anywhere. They continue oscillating. But if you ask where they are on average, you might say they're halfway between the two endpoints. And if you ask where they are after an even number of steps, you say at the start, and after an odd number, you say one step forward, and none of these answers is wrong. Each captures a different aspect of the situation, and Grandi's series is similar. Different questions about the series have different answers, and the paradox arises from expecting a single answer when the situation is inherently ambiguous, when the infinite oscillation resists reduction to a single number. The series continues, 1 minus 1 plus 1 minus 1, terms alternating forever, and the sum is 0 or 1 or 1/2 depending on how you calculate it, depending on what method you use, depending on what question you're really asking. And the paradox endures, a simple series that exposes deep issues about infinity, about summation, about the limits of algebraic manipulation, and about the need for careful definitions when dealing with infinite processes. And Grandi's series remains a teaching tool, a cautionary tale, a reminder that infinity is subtle, that divergent series require special handling, and that mathematics is not just calculation, but interpretation, not just following rules, but understanding when rules apply and when they break down. And the series oscillates, forever unresolved, forever producing different answers, and the paradox persists, elegant and instructive, a monument to the strangeness of infinity and the care required when extending finite concepts to the infinite realm. Libet's experiments. Paradox: why your brain decides before you do. A neuroscientist named Benjamin Libet designs an experiment to investigate the timing of conscious decision-making, to discover when conscious intention arises relative to brain activity and action. And subjects sit before a screen with a moving dot like a clock hand, and they are instructed to flex their wrist whenever they feel like it, spontaneously, without planning in advance, and while they watch the screen, they note the position of the dot when they first become aware of the intention to move, when they first consciously decide to flex. And meanwhile, electrodes measure brain activity, specifically measure the readiness potential, a build-up of neural activity that precedes voluntary movements. And Libet's finding is striking and controversial. The readiness potential begins several hundred milliseconds before the subject reports conscious awareness of the intention to move, the brain activity precedes conscious intention by about 300 to 500 milliseconds. And this seems to show that the brain decides to move before consciousness decides. That unconscious neural processes initiate the action, and conscious intention is a kind of afterthought, an epiphenomenon, something that arises after the decision has already been made at the unconscious level. And this finding appears to challenge free will, appears to show that conscious decisions do not cause actions but merely accompany them or follow them. And this is Libet's experiment's paradox, the discovery that our conscious intentions come too late to cause our actions, come after the brain has already committed to acting. And this creates philosophical puzzles about the nature of volition, about whether we truly initiate our actions or merely become aware of them after unconscious processes have already set them in motion. Imagine the subject in Libet's experiment, watching the dot move around the screen, waiting for the urge to flex their wrist, and suddenly they feel the intention. They become aware of wanting to move, they experience the conscious decision, and they note the position of the dot. And a moment later, their wrist flexes, and this sequence feels like the intention caused the movement, feels like they decided consciously and then acted. But the brain recordings tell a different story, show that neural activity associated with the movement began several hundred milliseconds before the conscious intention that the brain was preparing to move, before consciousness knew about it. And this temporal order suggests that consciousness does not initiate action, but only monitors it, only becomes aware of decisions that have already been made unconsciously. And if this is correct, then conscious free will is an illusion, is a feeling that arises after the fact, after unconscious processes have already determined what will happen. The paradox is that subjectively, we feel like we consciously decide and then act, feel like conscious intention is the cause of action, but objectively, the neural evidence suggests that unconscious processes cause both the action and the conscious intention, that consciousness is not in the driver's seat but is a passenger, observing but not controlling, and this disconnect between subjective experience and objective reality creates the paradox, makes us wonder whether free will is real or illusory, whether we are agents who initiate actions or spectators who witness actions that our brains have already decided to perform. Visualize the timeline. At time 0, the readiness potential begins. Unconscious neural activity starts building up. At time 300 milliseconds, the subject becomes consciously aware of the intention to move. At time 500 milliseconds, the movement occurs. And the critical question is what causes what? Does the conscious intention at 300 milliseconds cause the movement at 500? Or does the unconscious readiness potential at time 0 cause both the conscious intention and the movement? And Libet's data suggests the latter, suggests that unconscious brain activity is the real cause, is the initiator, and conscious intention is just another effect, another consequence of the unconscious process. And if this is right, then conscious will is causally inert, does not actually produce behavior, is epiphenomenal. Many philosophers and scientists have challenged Libet's interpretation. One response questions the measurement of conscious intention, argues that asking subjects to note when they became aware of intending is asking them to introspect a process that might not be accessible to introspection, and the reported time of intention might be inaccurate, might be systematically delayed, and subjects might become aware of intending earlier than they report, perhaps at the same time as the readiness potential begins. And if conscious awareness actually coincides with the readiness potential, then there is no paradox. Consciousness is part of the initiating process, not an afterthought. Another response distinguishes between different kinds of decisions, argues that Libet's experiments involve arbitrary decisions, spontaneous movements without specific goals or reasons, and these are not typical of the kinds of decisions we care about when discussing free will. And meaningful choices, choices based on deliberation and reasons, might involve different neural processes, might involve consciousness more centrally. And Libet's findings about arbitrary wrist flexions do not generalize to all decisions, do not show that conscious deliberation is always epiphenomenal, and free will might be preserved for rational choices even if spontaneous impulses are unconsciously initiated. A third response questions the interpretation of the readiness potential, argues that early neural activity does not necessarily represent a decision or commitment to act, but might represent preparation, might be part of the process of forming an intention rather than being the cause of intention, and consciousness might be involved throughout this process. And the readiness potential and conscious intention might be parts of a single, integrated process rather than separate causes. And Libet's interpretation assumes too sharp a separation between unconscious and conscious processes, treats them as competing causes when they might be cooperative aspects of a single decision-making system. Some philosophers embrace Libet's findings, argue that they confirm what we should have known all along, that consciousness does not have magical causal powers, that all mental processes are brain processes, and brain processes are physical processes that operate according to causal laws, and conscious states are aspects of brain states, not separate entities that somehow reach into the physical world to cause behavior. And Libet's experiments help dispel the Cartesian illusion that consciousness is a separate substance with independent causal power, help show that we are physical beings whose actions are caused by physical brain processes, and consciousness is part of this physical system, not a separate controller. Libet himself proposed that consciousness might not initiate actions, but might have a veto power, might be able to stop actions that unconscious processes have initiated. And he found some evidence for this, found that conscious intention could inhibit movements, even after the readiness potential had begun. And this veto function preserves a role for conscious will, makes consciousness a gatekeeper, if not an initiator. And this preserves some form of free will, free won't rather than free will, the ability to consciously inhibit unconsciously initiated impulses. The experiments have been repeated and refined by many researchers, with various results, some confirming Libet's findings and others qualifying them, showing that the relationship between brain activity, conscious awareness, and action is more complex than Libet's original interpretation suggested, and the debate continues with no consensus about what the experiments show about free will, about whether they undermine it or are compatible with it. And the paradox persists as a live issue in neuroscience and philosophy. The subject flexes their wrist, notes the time of intention, and the electrodes record the readiness potential, and the timing reveals that brain activity preceded awareness. And the question remains what this means for free will, whether it shows that consciousness is epiphenomenal, that we do not truly initiate our actions, or whether the interpretation is wrong, whether consciousness is involved earlier than subjects report, or whether the experiments test the wrong kinds of decisions. And Libet's paradox endures as one of the most discussed and controversial findings in the neuroscience of volition, a set of experiments that appears to show that free will is an illusion, that our conscious sense of agency is a feeling that arises after decisions have already been made, and whether this appearance is accurate, whether the paradox is real or illusory, remains one of the most important questions at the intersection of neuroscience and philosophy. And the readiness potential builds, and consciousness awakens, and action follows, and the temporal order creates the paradox, and the debate continues. Meinong's paradox, where non-existent objects live. A philosopher named Alexius Meinong proposes a strange theory, a theory about objects that do not exist, and Meinong argues that there are objects that do not exist, but still have properties, can be talked about, can be thought about, and these non-existent objects populate what Meinong calls the realm of being, a broader category than existence, and examples include the Golden Mountain, which does not exist but is golden and is a mountain, and the round square, which does not exist but is round and square, and Sherlock Holmes, who does not exist but is a detective and lives on Baker Street. And Meinong's theory says we can make true statements about these non-existent objects. Can say truly that the Golden Mountain is golden, even though no Golden Mountain exists. And this creates paradoxes, creates puzzles about the nature of reference and truth. Because how can statements about nothing be true? How can non-existent objects have properties? How can we refer to what does not exist? And this is Meinong's paradox, the puzzle about non-existent objects, about whether they are real in some sense, whether being is broader than existence, whether there are things that do not exist but still have some kind of reality. And this paradox has generated enormous discussion, has led some philosophers to defend Meinong's theory in modified form and others to reject it entirely, to argue that non-existent objects are impossible, are contradictions, and all objects that can be thought about must exist in some sense. Imagine thinking about Sherlock Holmes, picturing the detective, his deerstalker hat, his pipe, his address at 221B Baker Street, and you're thinking about something. Your thoughts have content, have an object, and that object is Sherlock Holmes. But Sherlock Holmes does not exist, was never a real person, is a fictional character invented by Arthur Conan Doyle. And so, what are you thinking about when you think about Sherlock Holmes? What is the object of your thought? And Meinong says the object is Sherlock Holmes himself, a non-existent object, an object that has properties like being a detective and living on Baker Street but lacks the property of existence. And this seems to make sense of how we can think about fictional characters, how we can make true statements about them, but it creates problems because it seems to commit us to a vast ontology of non-existent objects. All the fictional characters, all the impossible objects like round squares, all the merely possible objects that could exist but do not. And this ontology seems bloated, seems to violate parsimony, seems to multiply entities beyond necessity. The paradox sharpens when we consider impossible objects, objects like the round square, which is both round and square, and these properties are incompatible, cannot both be instantiated by a single object. And yet Meinong's theory seems to allow that the round square is both round and square, has both properties despite their incompatibility, and this violates the law of non-contradiction, seems to allow contradictions to be true. And Russell famously criticised Meinong for this, argued that the round square both exists and does not exist. Exists because it has properties and things with properties must exist to have them, and does not exist because that is part of its characterization. And this contradiction shows that Meinong's theory is incoherent, cannot be accepted, and non-existent objects are impossible, and all talk of them must be reinterpreted as talk of something else, talk of ideas or words or possible worlds, but not talk of actual non-existent objects. Visualize Meinong's ontology as having two realms, the realm of existence containing actual objects, like tables and mountains and people, and the realm of being containing all objects, including non-existent ones like golden mountains and fictional characters, and the realm of being is vastly larger, contains everything we can conceive, all possibilities and impossibilities, and only a tiny subset of being also has existence. And Meinong's theory says that statements can be true of objects in the realm of being whether or not those objects exist, and truth is not restricted to existing objects. And this solves certain puzzles about reference, about how we can refer to what does not exist, but creates the paradox of how non-existent objects can have properties, can be subjects of true predications when there is nothing there to have the properties. One response to Meinong's paradox rejects non-existent objects, adopts Russell's theory of descriptions, which analyzes statements about non-existent objects as existential statements that happen to be false, and the golden mountain is golden becomes. There exists something that is golden and is a mountain, and this statement is false because no such thing exists. And fictional statements are understood as prefixed by an implicit fiction operator. In the Sherlock Holmes stories, it is true that Holmes is a detective, and this preserves the intuition that Holmes is a detective, in some sense, while avoiding commitment to non-existent objects. And this Russellian approach has been standard in analytic philosophy, is the orthodox view, treats apparent reference to non-existent objects as disguised quantification or as occurring within the scope of intentional operators. Another response defends Meinong's theory in modified form, accepts that there are non-existent objects, but restricts what properties they can have, distinguishes between nuclear properties like being golden or being a detective, which non-existent objects can have, and extra-nuclear properties like existing or being thought about, which are different, and impossible objects like round squares have both roundness and squareness as nuclear properties, but do not violate contradiction because they do not exist, do not have instances in reality, and their properties do not need to be jointly instantiable. And this neo-Meinongian approach preserves some of Meinong's insights while avoiding Russell's objection, and various philosophers, including Terence Parsons and Richard Routley, have developed sophisticated neo-Meinongian theories that handle the paradoxes. A third response appeals to possible worlds, argues that fictional and non-existent objects exist in other possible worlds, are possible but not actual, and when we talk about Sherlock Holmes, we're talking about a possible person, someone who exists in other possible worlds, in worlds where Conan Doyle's stories are true, and this preserves the intuition that Holmes is a detective, is a real object in some sense, while avoiding the paradox of non-existent objects, because Holmes is not non-existent but merely non-actual, exists in other worlds. And possible worlds semantics provides a framework for understanding modality and fiction without Meinongian ontology. Meinong's paradox also raises questions about what it means to exist, about whether existence is a property like others or is somehow special, and Kant argued that existence is not a real predicate, not a property that objects have or lack, but is the presupposition of having properties. And this Kantian view seems to refute Meinong, seems to show that non-existent objects cannot have properties because having properties requires existing. But Meinongians respond that this assumes existence is necessary for predication, that only existing things can have properties, and this assumption is precisely what Meinong denies. And the debate continues about whether existence is a property and whether objects must exist to have properties. The Golden Mountain glitters in imagination, non-existent but golden, and Sherlock Holmes solves cases in fiction, non-existent but a detective, and the round square defies logic, non-existent and impossible, and Meinong's theory says these are real objects in the broad sense of being, and the paradox asks how this can be, how nothing can be something, how non-existence can have properties, and the answers divide philosophers, some accepting Meinong's insights, some rejecting them entirely, and the paradox persists as a challenge to theories of reference and ontology, a puzzle about what we talk about when we talk about what does not exist, and whether such talk requires real objects or can be explained without them. And Meinong's paradox endures as one of the strangest and most controversial problems in metaphysics, a problem about the boundary between being and non-being, about what counts as real, and about whether existence is the only kind of reality or whether non-existent objects have their own shadowy realm of being. Nagel's bat problem, why you can never know what it's like to be anything else. A philosopher contemplates a bat hanging upside down in a cave, navigating through echolocation, emitting high-frequency sounds and listening to the echoes, building a sonic map of the world. And the philosopher asks what it is like to be a bat. What is the subjective character of bat experience? What does echolocation feel like from the inside? And philosopher Thomas Nagel argues that no amount of objective information about bat neuroscience, about bat behavior, about the physics of sonar, can tell us what bat experience is like, because subjective experience has an essential first-person character, a what it is likeness that cannot be captured from the third-person objective perspective of science, and the gap between objective description and subjective experience is unbridgeable. And this means that consciousness, at least in its subjective aspect, resists scientific explanation, resists reduction to physical terms. And this is Nagel's bat problem, presented in his famous 1974 paper, What Is It Like to Be a Bat? And the problem illustrates the explanatory gap between physical facts and phenomenal facts, shows that subjective experience involves something that objective science cannot capture, and challenges physicalist theories of mind to explain how subjective character could be accommodated within a purely physical framework. Imagine trying to know what echolocation is like, trying to understand bat experience from the inside, and you learn all the objective facts. Learn about the bat's auditory system, about how it processes echoes, about which brain regions are involved. And this knowledge is real, is valuable, tells you how echolocation works, but it does not tell you what it feels like, does not give you access to the bat's subjective experience, to the phenomenology of navigating by sound. And Nagel's point is that this gap is not due to practical limitations, not due to insufficient technology or incomplete knowledge, but is a fundamental gap between objective and subjective perspectives, between what can be known from outside and what can only be known from inside. And no amount of objective knowledge can bridge this gap, can provide access to subjective experience. The bat problem generalizes beyond bats to any creature with a different sensory modality, a different nervous system, a different form of consciousness. And Nagel uses bats because they are mammals, are relatively similar to humans, yet have a sensory mode, echolocation, that humans lack. And this combination makes the example vivid, makes the gap between human and bat experience clear. And if we cannot know what it is like to be a bat, then we certainly cannot know what it is like to be a fish, an insect, an octopus, creatures whose nervous systems and sensory worlds are even more alien. And this suggests that consciousness, in its subjective aspect, is fundamentally private, is accessible only to the being who has it, and different kinds of consciousness are mutually inaccessible, cannot be fully understood from outside. Visualize the subjective character of experience as the view from inside, the first-person perspective, the what it is likeness. And this perspective is essential to consciousness, is what makes consciousness consciousness rather than merely information processing. And Nagel argues that physicalism, the view that everything is physical, must either deny that subjective character exists, which seems false because we all know from our own case that consciousness has a subjective character, or must explain how subjective character could be physical, how objective physical facts could constitute subjective, first-person experiences. And this explanation is what physicalism has not provided, what the bat problem challenges physicalism to provide. One response to the bat problem accepts the explanatory gap, but denies that it shows anything metaphysical, argues that the gap is merely epistemological, is about the limits of what we can know rather than about the nature of reality, and consciousness might be physical even though we cannot fully understand it from the objective third-person perspective. And just as we cannot know what it is like to be a bat, we also cannot know what it is like to be another human, cannot fully access their subjective experiences, and yet we do not conclude that human consciousness is non-physical. And so the bat problem shows limits of knowledge, but not limits of physicalism, shows that subjective experience has aspects that resist objective description, but not that these aspects are non-physical. Another response argues that future science might bridge the gap, might develop ways of understanding subjective character objectively, might create theories that capture phenomenology in physical terms, and our current inability to imagine how this could be done does not prove that it cannot be done. And Nagel's argument trades on current ignorance, assumes that the gap is permanent when it might be merely temporary. And this response is optimistic about the prospects for physicalist explanations of consciousness, believes that the hard problem and the bat problem will eventually be solved by scientific progress. A third response from Nagel's position argues that the bat problem reveals something deep about the structure of reality, that consciousness has an irreducibly subjective aspect, an aspect that cannot be captured by objective physical description. And this does not mean consciousness is non-physical in the sense of being immaterial or supernatural, but it means that physicalism, as traditionally conceived, is incomplete, misses something essential about consciousness, and a complete theory of reality must include both objective physical facts and subjective phenomenal facts. And these two kinds of facts cannot be reduced to each other. And this position is sometimes called naturalistic dualism, accepts that consciousness is natural, is part of the natural world, but denies that it is reducible to physics. The bat problem also has implications for artificial intelligence, for whether machines could be conscious, because if we cannot know what it is like to be a bat, then we also cannot know what it is like to be a computer, cannot know whether AI systems have subjective experiences, and the bat problem suggests that behavioral evidence is insufficient, that even if a machine passes every behavioral test, exhibits intelligence, responds appropriately to stimuli, we still cannot know whether there is something it is like to be that machine, whether there is subjective experience behind the behavior, and this creates a permanent epistemic barrier, a limit on what we can know about machine consciousness. The bat hangs in the cave, emitting sounds, perceiving the world through echoes, and its experience is alien, is inaccessible to human understanding. And Nagel's question remains, what is it like? And the answer is we do not know, cannot know, because knowing requires access to the subjective perspective, requires being the bat or having the bat's sensory and cognitive capacities, and neither is possible. And so bat consciousness remains a mystery, remains forever beyond human comprehension. And this mystery is not unique to bats but applies to all consciousness, to the fundamental subjectivity of experience, to the what it is likeness that defines phenomenal consciousness. And Nagel's bat problem endures as one of the most influential thought experiments in philosophy of mind, a vivid illustration of the explanatory gap, a challenge to physicalist theories, and a reminder that consciousness, in its subjective aspect, resists objective description, resists scientific reduction, and remains one of the deepest puzzles about the nature of mind and reality. And the bat flies through the cave, navigating by sound, living its bat life, having its bat experiences, and what those experiences are like remains unknown, remains unknowable. And the problem persists, the gap between objective knowledge and subjective experience, the difference between knowing about consciousness and knowing consciousness from the inside. And Nagel's question echoes, what is it like to be a bat? And no answer comes, no answer can come, and the problem stands as a permanent marker of the limits of objective understanding, the irreducible subjectivity of experience and the mystery at the heart of consciousness. Quine's Gavagai problem, why we can never know what anyone really means. An anthropologist arrives in a remote village to study an unknown language, a language no outsider has encountered before. And the anthropologist has no translator, no dictionary, no common linguistic framework, only observations and patience, and the method is radical translation. Learning the language from scratch by observing how natives use words in response to events. And one day, a rabbit runs past and a native points and says Gavagai, and the anthropologist writes in the notebook, Gavagai means rabbit. And this seems reasonable, seems like an obvious inference. The native saw a rabbit and said Gavagai, so Gavagai must refer to rabbits. But philosopher Willard Van Orman Quine points out a problem, a deep problem about meaning and translation. Because Gavagai might mean rabbit, but it might also mean undetached rabbit part, or rabbit stage, or collection of rabbit molecules, or instance of rabbithood. And all these translations are consistent with the native's behaviour. All would lead the native to say gavagai in exactly the same circumstances, whenever a rabbit is present, and there is no fact of the matter, no objective truth about which translation is correct, no way to determine what gavagai really means. And this indeterminacy is not due to practical limitations, not due to insufficient evidence, but is fundamental, is a consequence of how meaning works. And this is Quine's gavagai problem, also called the problem of indeterminacy of translation, a challenge to the idea that words have determinate meanings, that translation has right answers, and that we can know what others mean when they speak. Imagine trying to distinguish between gavagai means rabbit and gavagai means undetached rabbit part. And you point to the rabbit and the native says gavagai, and you point to the rabbit's ear and ask whether this is gavagai, and the native responds, but you do not know whether the response means yes because the ear is an undetached rabbit part, or no, because the ear is not a whole rabbit, or something else entirely. And every test you design, every question you ask, can be interpreted in multiple ways, can be answered consistently by multiple translations, and no amount of observation, no behavioural evidence can definitively settle which translation is correct, because the native's behaviour under all possible circumstances is compatible with multiple interpretations. And Quine argues that this shows meaning is indeterminate, that there is no fact about what gavagai really means, only different translation manuals that work equally well, that map the native's language onto ours in different but equally legitimate ways. The problem generalizes beyond anthropology to all understanding of language, because even when we share a language, even when we both speak English, the gavagai problem applies. We cannot be certain that we mean the same thing by our words, that rabbit means to you what it means to me. We might be using different concepts, carved up differently, but our behavior is similar enough that we never notice the difference. And this raises the disturbing possibility that communication is always partial, always approximate, that we never fully understand each other, that meaning is not something objective that words have, but something we impose through interpretation, and different interpretations can fit the evidence equally well, and there is no transcendent perspective from which to judge which interpretation is correct. Visualize meaning as a relationship between words and world, and Quine's point is that this relationship is underdetermined by behaviour, by the evidence available to translators, because infinitely many relationships are consistent with the same behavioural evidence. Infinitely many ways of mapping words to world produce the same observable patterns, and choosing among these possibilities requires going beyond evidence, requires making decisions that are not forced by facts, and these decisions constitute meaning rather than discovering it. And so meaning is partially conventional, partially stipulated, not fully determined by reality. The gavagai problem challenges referential theories of meaning, theories that say words mean things because they refer to objects in the world, because rabbit refers to rabbits, and water refers to water, and Quine's argument shows that reference is inscrutable, cannot be determined from behaviour alone, because words can be interpreted as referring to different things, different ways of carving up reality, and all interpretations fit the evidence, and so reference is not an objective relation, but is relative to a translation manual, relative to a scheme of interpretation, and different manuals. Different schemes can assign different references to the same words while remaining equally correct. One response to the gavagai problem accepts the indeterminacy, embraces it as a truth about meaning, argues that Quine is right, that there is no fact of the matter about what words mean beyond what is determined by behavioural evidence, and meaning is holistic, depends on the entire network of beliefs and language practices. And translation manuals are theoretical frameworks that organise this evidence. And like all theories, they are underdetermined by data, and multiple theories fit the same data equally well. And choosing among them involves pragmatic considerations, simplicity, utility, coherence, but not truth in any absolute sense. And this response treats meaning as a human construction, something we create through practices rather than something we discover in nature. Another response denies the indeterminacy, argues that Quine's thought experiment is artificial, that in real translation situations additional evidence is available, evidence about intentions, about how speakers correct each other, about the structure of their conceptual schemes. And this additional evidence narrows down the possibilities, rules out bizarre interpretations like undetached rabbit part, and determines that Gavagai means rabbit in the ordinary sense. And while perfect certainty may be impossible, practical determinacy is achievable, and meaning is objective enough for communication to succeed, for translation to have right and wrong answers. And the Gavagai problem is an epistemological worry, a concern about how we know what words mean, but it does not show that words lack determinate meanings, only that discovering those meanings is difficult. A third response appeals to charity, to the principle that we should interpret speakers as making sense, as having coherent beliefs, as speaking truly most of the time. And this principle constrains translation, rules out interpretations that make speakers irrational or massively mistaken. And while charity does not uniquely determine translation, it narrows the range of acceptable interpretations, and combined with simplicity and other pragmatic virtues, it makes translation tractable, makes it possible to arrive at good translations, even if not perfect ones. And this response treats translation as an interpretive practice, guided by norms rather than as a purely empirical investigation, guided only by behaviour. The Gavagai problem also connects to broader philosophical issues about realism and anti-realism, about whether there are objective facts independent of our theories and languages. Because if meaning is indeterminate, then perhaps reality itself is indeterminate. Perhaps there is no fact about whether rabbits or undetached rabbit parts exist, only different ways of organising experience, different conceptual schemes that carve up the world differently. And Quine's ontological relativity, his claim that what objects exist is relative to a language or theory, follows from the Gavagai problem, from the recognition that reference is inscrutable, that we cannot say what exists absolutely, but only what exists relative to a framework. The anthropologist sits with a notebook, the word Gavagai recorded, the translation uncertain, and the native speaks, and the anthropologist interprets, and communication proceeds approximately, pragmatically, successfully enough for practical purposes, and whether Gavagai really means rabbit or something else remains undetermined, remains a question without an answer. And Quine's problem persists, not as a practical obstacle to translation, but as a philosophical challenge to theories of meaning, as a demonstration that meaning is more elusive than we thought, more dependent on interpretation and less determined by facts. And the Gavagai problem endures as one of Quine's most influential contributions, a thought experiment that changed how philosophers think about language, about meaning, about translation, and about the relationship between words and world. And the problem remains unsolved, perhaps unsolvable, a permanent feature of linguistic philosophy, a reminder that understanding each other is harder than it seems, that meaning is indeterminate, that communication is an achievement rather than an automatic consequence of shared language, and that the gap between what we say and what we mean, between our words and their reference, can never be fully closed. And the rabbit runs past and the native says, Gavagai, and we translate approximately, hopefully, never quite certain that we have understood. Skolem's paradox. Set theory describes infinite sets of different sizes, and Georg Cantor proved that the real numbers are uncountably infinite, that they cannot be placed in one-to-one correspondence with the natural numbers, that there are more real numbers than natural numbers. And this is one of the foundational results of modern mathematics, a theorem that establishes a hierarchy of infinities. But Thoralf Skolem discovered a paradox, or what appears to be a paradox, that threatens this result. And the paradox is that any consistent first-order theory that has an infinite model also has a countable model, a model where the domain consists of only countably many elements. And this is the Löwenheim-Skolem theorem, and applying it to set theory yields a troubling conclusion. If set theory is consistent, then it has a countable model, a model where the universe of sets is countably infinite. And yet within this model, the axioms of set theory are satisfied, including Cantor's theorem, which proves that the real numbers are uncountable. And so we have a countable model of set theory in which there exists an uncountable set. And this seems contradictory. How can a set be uncountable if the entire universe is countable? How can there be more real numbers than natural numbers if the whole model has only countably many elements? And this is Skolem's paradox. The resolution lies in understanding the distinction between internal and external perspectives, between how things appear from inside the model and how they appear from outside. From inside the countable model of set theory, all the axioms hold. Cantor's theorem is provable. The real numbers have no enumeration within the model. No bijection between the reals and the naturals exists as far as the model is concerned. And so internally, the reals are uncountable. But from outside the model, from the perspective of someone who can see the entire structure, the model itself has only countably many elements, and there exists a bijection between the elements of the model and the natural numbers. A bijection that is not itself an element of the model, that does not correspond to any set or function within the model. And so externally, the model is countable. And this distinction between internal and external is the key to resolving the paradox. Uncountability is relative. It depends on what bijections are available, and different models have different bijections. Skolem's paradox reveals something profound about the nature of mathematical existence and the limits of first-order logic. It shows that first-order logic cannot pin down the cardinality of infinite sets, that the concept of uncountability is not absolute but relative to a model, that what counts as uncountable in one model may be countable in another, and this relativity is a consequence of the expressive limitations of first-order logic, which can only quantify over elements of the domain, not over arbitrary functions or sets of elements. And so first-order set theory cannot express the existence of a bijection between two sets in an absolute way, cannot say, in a model-independent manner, that a set is countable or uncountable. Some philosophers and logicians find this relativity troubling, a sign that first-order set theory is inadequate as a foundation for mathematics, that a stronger logic, perhaps second-order logic, which allows quantification over sets and functions, is needed to capture the intended meaning of set theoretic concepts. And in second-order logic, the Löwenheim-Skolem theorem does not hold. There are categorical characterizations of structures, including characterizations of the natural numbers and the real numbers that pin down their cardinality uniquely. And so second-order logic avoids Skolem's paradox by being more expressive, by allowing statements that distinguish countable from uncountable models. But second-order logic has its own difficulties. It lacks complete proof systems. There is no algorithmic procedure that can, in principle, prove all second-order truths. And so the gain in expressiveness comes at the cost of losing some of the nice logical properties that first-order logic enjoys. Others embrace the relativity revealed by Skolem's paradox, arguing that it shows the conventional or perspectival nature of mathematical concepts, that cardinality is not an intrinsic property of sets but a relation between sets and models, that what we call uncountable is simply a set that lacks an enumeration within a particular model, and that different models can disagree about what is countable without any of them being wrong. And this perspective aligns with a pluralistic or model-theoretic approach to mathematics, where there is no single intended model of set theory, but many models, each with its own internal structure, and what is true varies from model to model, and mathematical truth is relative to a choice of model. Skolем's paradox also connects to issues about the definiteness of the continuum, about whether the set of real numbers has a well-defined cardinality, and the continuum hypothesis, which asks whether there is a set whose cardinality is strictly between that of the natural numbers and the real numbers. And this hypothesis is independent of the standard axioms of set theory, meaning that neither the hypothesis nor its negation can be proven from the axioms. And some mathematicians interpret this independence as evidence that the cardinality of the continuum is not a definite matter of fact, but depends on additional assumptions or on the choice of model. And Skolем's paradox reinforces this interpretation by showing that even the distinction between countable and uncountable is model dependent. The paradox remains a touchstone in the philosophy of mathematics and the foundations of logic. It illustrates the limits of first-order logic, the relativity of model-theoretic notions, and the gap between formal systems and intended interpretations. And it forces careful thinking about what it means to say that a set is countable or uncountable, about whether mathematical concepts have absolute meanings or are always relative to a framework, and about the relationship between syntactic provability and semantic truth. And the paradox has no simple resolution. Different philosophers and mathematicians draw different lessons, some seeing it as a defect of first-order logic, others as a feature revealing deep truths about the nature of infinity and cardinality. And the debate continues, with implications for how we understand the foundations of mathematics, the status of set theory, and the nature of mathematical truth. The countable model sits in logical space, containing sets and functions and real numbers, and within this model, Cantor's theorem holds. The reals are uncountable, no enumeration exists, but from outside the model, the whole structure is countable. All its elements can be listed, and the real numbers of the model, uncountable internally, are countable externally. And this doubling of perspective, this split between internal and external, is the heart of Skolем's paradox, a demonstration that perspective matters, that truth is not always absolute, that models can disagree, and that first-order logic, powerful as it is, cannot capture all the nuances of infinite cardinality. And the paradox endures, a puzzle that has shaped logic and set theory, a challenge that continues to generate discussion and debate, and a reminder that even the most basic mathematical concepts, even the notion of how many, become subtle and contested when applied to infinite collections. The Allais paradox. Maurice Allais, a French economist and Nobel laureate, presented a pair of choices in 1953 that revealed a systematic pattern of preferences violating the independence axiom of expected utility theory, and this became known as the Allais paradox, one of the most influential demonstrations that human decision-making deviates from the prescriptions of standard rational choice theory. And the paradox shows that people's preferences can be influenced by irrelevant alternatives, by outcomes that occur in both options and should therefore cancel out, yet somehow affect which option is chosen. The first choice involves two lotteries. Lottery A offers a certain gain of $1 million, while Lottery B offers a 10% chance of winning $5 million, an 89% chance of winning $1 million, and a 1% chance of winning nothing. And when faced with this choice, most people prefer Lottery A, the certain million, preferring the sure thing to the gamble, even though the gamble has a higher expected value. And this preference reflects risk aversion, a common and generally accepted feature of human decision-making. The second choice involves two different lotteries. Lottery C offers an 11% chance of winning $1 million and an 89% chance of winning nothing, while Lottery D offers a 10% chance of winning $5 million and a 90% chance of winning nothing. And when faced with this choice, most people prefer Lottery D, the gamble with the higher potential payoff, accepting the slightly lower probability of winning in exchange for the much larger prize. The paradox emerges when these two preference patterns are analysed together, because the independence axiom of expected utility theory requires that if lottery A is preferred to lottery B, then lottery C should be preferred to lottery D. And the reason is that lotteries A and B differ from lotteries C and D only in that there is an 89% chance in both A and B of receiving $1 million, and in both C and D this 89% outcome is replaced with winning nothing, and this replacement should affect both lotteries equally, should not change the preference order, because the independence axiom says that preferences between lotteries should depend only on outcomes where the lotteries differ, not on outcomes that are the same in both. And the 89% probability mass is shifted in the same way for both pairs, and so if you prefer A to B, you should also prefer C to D. And if you prefer D to C, you should also prefer B to A. The typical pattern of preferences, A over B and D over C, cannot be represented by any utility function satisfying the expected utility axioms. And so the Allais paradox demonstrates that people systematically violate the independence axiom, that their preferences are sensitive to common outcomes in ways that expected utility theory does not permit. And this violation is robust, appearing in experiments with diverse populations, with real monetary stakes, with careful experimental design, and the paradox cannot be dismissed as error or confusion, but represents a genuine feature of human decision-making. The paradox has inspired alternative theories that can accommodate the observed preferences, including prospect theory, developed by Daniel Kahneman and Amos Tversky, which modifies expected utility theory by introducing reference points, by treating gains and losses differently, by allowing for probability weighting where people overweight small probabilities and underweight large probabilities. And these modifications can explain the Allais preferences, because in the first choice, the certainty of $1 million receives extra weight, making lottery A more attractive, while in the second choice the small probabilities are overweighted, making the 10% chance of $5 million in lottery D seem more appealing than the 11% chance of $1 million in lottery C. Other theories include regret theory, where people anticipate the regret they would feel if they made the wrong choice. And this anticipated regret influences preferences in ways that violate independence, because the certain million in lottery A avoids the regret of choosing the gamble and losing everything, while the choices between C and D do not have this asymmetry. And rank-dependent utility theory, which generalizes expected utility by allowing the utility of lotteries to depend not just on outcomes and probabilities, but on the rank ordering of outcomes, and this allows for preferences that violate independence while maintaining other desirable properties. The Allais paradox raises normative questions about rationality. Some argue that the independence axiom is a fundamental requirement of rational choice, that violating it leads to incoherence, to preferences that can be exploited through Dutch books or money pumps, to decision-making that is systematically suboptimal, and that people who exhibit Allais preferences are making mistakes and should revise their preferences to conform to expected utility theory. While others argue that the independence axiom, while mathematically convenient, is not a necessary condition for rationality, that it does not capture important aspects of how people value uncertain prospects, that preferences like those in the Allais paradox reflect legitimate concerns about certainty, regret, and the context of choice, and that we should revise our normative theories to accommodate these preferences rather than dismissing them as irrational. The paradox also has practical implications for economics and policy, because if people systematically violate independence, then markets may not function as standard theory predicts. Risk preferences may be context-dependent. Insurance and investment decisions may be influenced by framing effects, and policies designed to maximize expected utility may not align with what people actually prefer. And understanding these deviations from expected utility helps explain phenomena like the equity premium puzzle, the disposition effect, and other anomalies in financial markets and economic behavior. The lotteries sit before you, the choices must be made, and your preferences, revealed through your choices, tell a story about how you value certainty and risk, about how you weigh probabilities and outcomes, and the story violates the axioms of rational choice, violates the clean mathematical structure of expected utility theory, and yet the choices feel reasonable, feel justified, feel like they reflect something important about value and uncertainty that the theory misses, and the paradox persists. The gap between theory and behavior remains. The independence axiom is violated again and again in experiments and in life, and decision theorists must choose. Either insist that the axiom is normatively binding and that violators are irrational, or acknowledge that the axiom is too strong, that rational choice is more complex than expected utility allows, and that new theories are needed to capture the richness of human decision-making. And the Allais paradox remains a landmark, a decisive demonstration that classical rational choice theory does not fully describe or prescribe human behavior, a challenge that spawned new theories and new research programs, and a reminder that rationality is contested, that what counts as a reasonable choice depends on assumptions and frameworks that are themselves open to question, and the lotteries remain, the choices remain, the preferences remain, and the paradox endures, unsolved in the sense that no consensus has emerged about whether the preferences are rational or irrational, about whether we should revise our theories or our preferences, about whether independence is a negotiable axiom or a non-negotiable requirement. And the debate continues. Philosophers and economists and psychologists arguing about what rationality requires, about what humans actually do, and about the relationship between these two questions. The Banach-Tarski paradox. A solid sphere can be decomposed into a finite number of pieces, which can then be reassembled using only rotations and translations to form two solid spheres, each identical to the original. And this seems to violate conservation of volume, seems to create matter from nothing, seems to be impossible, and yet it is a theorem in mathematics, proven rigorously using the axiom of choice and the properties of infinite point sets. And this is the Banach-Tarski paradox, named after Stefan Banach and Alfred Tarski, who proved it in 1924. And the paradox reveals deep and counterintuitive features of infinite decompositions, of non-measurable sets, and of the relationship between mathematics and physical reality. The proof proceeds by decomposing the sphere into a finite number of pieces, typically 5 or 6, and each piece is a set of points, not a solid region with smooth boundaries, but a scattered, disconnected, infinitely complex collection of points. And these pieces are non-measurable, meaning they do not have well-defined volumes in the usual sense. They cannot be assigned a size using standard measure theory, and this is crucial because measurable sets cannot be duplicated. Conservation of volume holds for measurable sets, but non-measurable sets escape this constraint. They can be rearranged in ways that seem to violate intuition, and the Banach-Tarski paradox exploits this by constructing pieces that are so pathological, so wildly scattered, that they can be rotated and translated to form two complete spheres. The decomposition uses the axiom of choice, the principle that given any collection of non-empty sets, there exists a way to choose one element from each set, and the axiom of choice is independent of the other axioms of set theory. It cannot be proven or disproven from the standard axioms, and some mathematicians reject it precisely because it leads to results, like the Banach-Tarski paradox, results that seem absurd, and rejecting the axiom of choice avoids the paradox. But it also cripples large parts of modern mathematics. Many important theorems depend on the axiom of choice, and most mathematicians accept it despite its counterintuitive consequences. The paradox applies only to objects in 3-dimensional space, or higher. It does not work in 2 dimensions. A disk cannot be decomposed and reassembled into two disks. And this is because the group of rotations in the plane is amenable, meaning it admits a certain kind of averaging that prevents paradoxical decompositions, while the group of rotations in three-dimensional space is non-amenable, and this non-amenability is what makes the Banach-Tarski paradox possible. The fact that rotations in 3 dimensions can be combined in ways that allow pieces to be moved around and duplicated. The paradox raises questions about the relationship between mathematical objects and physical objects, because while the Banach-Tarski theorem is mathematically rigorous, it does not imply that a physical sphere can be duplicated. The decomposition involves infinitely complex sets, pieces that are not solid regions but scattered collections of points, with no smooth boundaries, and such pieces cannot be physically realized, cannot be cut or manipulated, and so the paradox is a feature of mathematical idealizations rather than a claim about physical reality. And this distinction is important. The paradox shows that mathematical spheres treated as sets of points behave in strange ways, but it does not threaten conservation of mass or energy in physics, because physical objects are not sets of points but arrangements of atoms or fields or quantum states, and these are governed by physical laws that do not permit paradoxical duplication. Some mathematicians and philosophers argue that the Banach-Tarski paradox is not really a paradox but a theorem, a surprising result that reveals features of infinite point sets and non-measurable sets, and that calling it a paradox is misleading, suggesting contradiction when there is none, only counterintuitive behavior. And from this perspective, the paradox is valuable precisely because it challenges intuition, because it shows that infinite collections have properties that finite collections lack, that measure theory has limits, that the axiom of choice has strange consequences, and that mathematics is richer and stranger than naive expectations suggest. Others find the paradox troubling, a sign that something is wrong with the foundations, that the axiom of choice should be rejected or restricted, that non-measurable sets are pathological objects that should not be admitted into mathematics, and that theories which avoid such sets, like those based on constructive or intuitionistic logic, provide better foundations. And this debate reflects deeper disagreements about the nature of mathematical existence, about what kinds of objects mathematics should study, and about the role of intuition in guiding mathematical practice. The Banach-Tarski paradox also appears in discussions of probability and decision theory, because if a sphere can be decomposed into non-measurable pieces, then probability distributions on spheres must be carefully defined to avoid assigning probabilities to non-measurable sets. And this technical requirement reflects the same underlying issue, that not all collections of points can be measured, that probability requires measurability, and that attempting to assign probabilities to arbitrary sets leads to contradictions or paradoxes. The sphere sits on the table, solid and indivisible to the eye, but mathematically it is a set of infinitely many points. And the Banach-Tarski theorem says that these points can be partitioned into pieces, 5 or 6 strange scattered collections, and these pieces can be moved, rotated, and translated, and reassembled into 2 spheres, identical to the original. And the volume has doubled, or seems to have doubled, but the pieces never had well-defined volumes. They were never measurable, and so nothing has been created, no conservation law has been violated, only the intuition that decomposition preserves size, and this intuition holds for finite decompositions, for measurable pieces, but fails for infinite non-measurable pieces, and the paradox endures. A theorem that sounds impossible, a result that challenges understanding, a demonstration that mathematics contains surprises, that infinity is stranger than imagination, that point sets behave in ways that solid objects do not, and that the axiom of choice, innocent as it seems, permits constructions that defy common sense, and the sphere duplicates, mathematically, if not physically. And the paradox remains a permanent fixture in the landscape of mathematics, a result that students encounter with disbelief, that mathematicians accept as rigorous yet counterintuitive, and that philosophers debate as revealing something deep about the nature of mathematical objects, about the limits of measure theory, about the relationship between infinite idealization and finite reality. And the sphere sits there, unchanged and yet somehow doubled, a monument to the strangeness of infinity, to the power of the axiom of choice, and to the capacity of mathematics to prove truths that seem like impossibilities. The binding problem: how your brain unites what it processes separately. A neuroscientist examines how the brain processes visual information, discovers that different features of objects are processed in different brain regions. Color is processed in one area, motion in another, shape in a third, orientation in a fourth, and all these features are analyzed separately, by specialized modules, by distinct populations of neurons. And yet when you look at a red ball moving to the right, you do not experience color, motion, and shape as separate. Do not see redness here and roundness there and rightward motion elsewhere, but see a unified object, a red round ball moving right, and all the features are bound together, are experienced as properties of a single thing. And this creates the binding problem, the puzzle of how the brain, which processes features separately, creates unified conscious experiences, how separate neural processes give rise to integrated perception, how the many become one. And this problem is fundamental, touches on the nature of consciousness, on how neural activity becomes experience, on what unifies experience into coherent wholes, and no complete solution exists. Various theories have been proposed, but the binding problem remains one of the deep mysteries of neuroscience, a gap between our understanding of neural processing and our understanding of consciousness. Imagine the visual system as a factory, with different departments processing different aspects of the product. One department handles color, another handles shape, another handles location, and all work in parallel, all process simultaneously, and each department produces its output color information, shape information, location information, and somehow these separate outputs must be combined, must be integrated into a unified representation, must be bound together so that you experience a red ball rather than redness and roundness as separate unlocalized features. And the binding problem asks how this combination occurs, what mechanism ensures that the right features are bound together, that the redness is attributed to the round object and not to the square object that happens to be present in the scene. And this correct attribution, this accurate binding, is critical for coherent perception, for navigating the world successfully, and yet how the brain achieves it remains unclear. The binding problem has two aspects: the feature binding problem, which asks how different features of the same object are bound together, and the object binding problem, which asks how different objects are kept separate, are not confused with each other, and both aspects are challenging. Both reveal that perceptual unity is not given automatically by neural processing, but requires some mechanism, some process that groups features appropriately, and various mechanisms have been proposed. Attention has been suggested as a solution. The idea that attention binds features, that attended objects have their features integrated, while unattended objects do not. And this explains why feature binding errors occur when attention is diverted, why illusory conjunctions occur where features from different objects are misbound, are attributed incorrectly. Visualize attention as a spotlight that illuminates objects one at a time, and within the spotlight features are bound, are integrated, and outside the spotlight features remain separate, are not integrated. And this attentional binding theory has some support, has experimental evidence showing that feature binding requires attention, that without attention, features can be perceived separately without being bound correctly, and illusory conjunctions are more common under conditions of inattention, supporting the idea that attention is necessary for binding. But attention cannot be the complete solution, because some binding occurs pre-attentively. Some feature integration happens automatically before attention is applied, and so attention is part of the story, but not the whole story. Another proposed mechanism is temporal synchrony, the idea that neurons representing features of the same object fire in synchrony, fire together, and this synchrony is the binding code, is what marks features as belonging together and neurons representing different objects, fire at different times or with different phases, and this temporal separation keeps objects distinct, prevents their features from being bound together. And this synchrony theory has been influential, has generated extensive research, has led to discovery of synchronized neural oscillations in visual cortex, but the theory faces challenges. It is not clear that synchrony is sufficient for binding, it is not clear that consciousness depends on synchrony, and some experiments have failed to find the predicted correlations between synchrony and perceptual binding, and the theory remains controversial. A third approach argues that binding occurs through convergence, through hierarchical processing, where features are combined in higher-level areas, and early visual areas process features separately, but project to higher areas that represent combinations, that have neurons responding to specific conjunctions of features. And these conjunction neurons represent bound objects, represent integrated wholes, and binding is achieved through this hierarchical architecture, through neurons that explicitly encode feature combinations. And this approach has support from single neuron recordings showing that higher visual areas have neurons with complex selectivity, neurons that respond to specific combinations of shape and color and motion, and these neurons could be the neural basis of bound object representations. The binding problem also connects to consciousness, because unified conscious experience seems to require binding, seems to require that separate neural processes be integrated into coherent wholes, and some theories of consciousness, like integrated information theory, make integration central, argue that consciousness arises from integrated information, from systems where different parts interact and constrain each other, and binding as a form of integration is the combination of separately processed features into unified representations. And understanding binding may be crucial for understanding consciousness, may reveal how neural processes give rise to unified experience. The problem also has practical implications. For understanding neurological conditions where binding fails, where patients see features but cannot bind them correctly, and such conditions exist. Balint syndrome is one example, where patients can see individual features but cannot perceive objects, cannot integrate features into wholes. And these patients provide evidence that binding is a genuine process, is not automatic, can be disrupted by brain damage. And studying these patients helps understand normal binding, helps identify the brain regions and processes necessary for feature integration. Some philosophers argue that the binding problem is really a problem about consciousness, about how physical processes give rise to subjective experience, about the hard problem, and binding is one aspect of this, is the problem of how separate neural processes give rise to unified conscious experiences. And solving the binding problem may require solving the hard problem, may require understanding how neural activity becomes experience. And this makes binding one of the deepest problems in neuroscience, a problem at the interface between neuroscience and philosophy of mind. The brain processes features separately, color here, motion there, shape elsewhere, and yet you see unified objects, see red round balls moving, see integrated wholes, and how this integration occurs, how the separate processes give rise to unified experiences, remains one of the great unsolved problems. The binding problem stands, challenging, fundamental, revealing a gap between our understanding of neural processing and our understanding of perception. And various theories exist, various mechanisms have been proposed. Attention, synchrony, convergence, but no theory is complete. No theory explains all aspects of binding. and the problem persists as one of neuroscience's deepest mysteries. A puzzle about how unity emerges from multiplicity, how the brain binds what it processes separately, and the question remains open. The mechanism remains elusive, and the binding problem endures. The bystander effect. Why more witnesses mean less help. A woman screams in the street, attacked by an assailant, stabbed repeatedly over the course of 30 minutes. And dozens of neighbours hear the screams, look out their windows, witness the attack, and no one calls police, no one intervenes, no one helps, and the woman dies while witnesses watch. And this is the murder of Kitty Genovese in 1964, an event that shocked the public, that seemed to reveal something disturbing about urban indifference, about human nature, and psychologists John Darley and Bibb Latané investigated, conducted experiments to understand why bystanders fail to help, and their research revealed the bystander effect, the paradoxical finding that the presence of other witnesses decreases the likelihood that any individual will help, that the more people who witness an emergency, the less likely anyone is to intervene. And this contradicts common sense, which suggests that more witnesses mean more help, mean more potential helpers. But the psychological reality is opposite, is that responsibility diffuses across bystanders, that each assumes someone else will help. That pluralistic ignorance emerges where everyone looks to others to define the situation, and everyone concludes it must not be serious because no one else is acting, and the bystander effect reveals how social dynamics can produce collective inaction, can create situations where groups of people fail to help when any individual alone would help. And the effect has been replicated across hundreds of studies, has been demonstrated in contexts from emergencies to everyday helping, and understanding the bystander effect has practical implications for promoting helping behaviour, for overcoming diffusion of responsibility, for recognising that crowds do not guarantee help but often prevent it. Imagine witnessing an emergency. Someone collapses on the sidewalk, and you are alone, and your responsibility is clear, is unambiguous. There is no one else who could help, and so you help, you call for medical assistance, you check if the person is breathing, you do what you can, and the situation is straightforward. Responsibility is concentrated, is entirely yours. But now imagine the same situation in a crowded plaza. Dozens of people are present, all witness the collapse, and now responsibility is diffused, is distributed across all present, and you reason that someone else will help, that someone with more expertise will intervene, that surely someone has already called for help, and you look to others to see how they are reacting, and they are not panicking, are not rushing to help, and so you conclude perhaps the situation is not serious, perhaps the person is drunk rather than injured, perhaps help is not needed, and everyone reasons this way. Everyone diffuses responsibility, everyone looks to others and no one helps, and the person lies there untended while a crowd watches. And this is the bystander effect in action, the paradoxical result that more witnesses produce less help. The bystander effect demonstrates several psychological mechanisms: diffusion of responsibility, where the presence of others makes each individual feel less personally responsible; pluralistic ignorance, where everyone looks to others to define the situation, and everyone's inaction convinces everyone else that the situation is not serious; evaluation apprehension, where people fear being embarrassed if they help inappropriately, fear looking foolish if they misinterpret the situation; and audience inhibition, where the presence of others makes people self-conscious, makes them less willing to act. And these mechanisms combine to suppress helping behaviour, to create barriers that are stronger when more people are present, and the effect is not universal, is moderated by various factors, by the ambiguity of the situation, by whether the victim and bystander are similar, by time pressure, by the relationship between bystanders, but the basic pattern is robust, is well established. More bystanders generally mean less help. Visualize the effect as an inverse relationship. As bystanders increase, helping probability decreases, and experiments show this quantitatively. show that when participants believe they are the only witness, they help more than 80% of the time. But when they believe there are 4 other witnesses, they help less than 40% of the time, and response time increases with number of bystanders. It takes longer to help when more are present, and these effects are not small, are not marginal, are dramatic reductions in helping behaviour caused simply by the presence of others. And the effect challenges the assumption that safety in numbers applies to emergencies, shows that crowds can be dangerous not because they contain threats, but because they inhibit helping. One implication of the bystander effect is for personal safety, for recognising that if you need help in an emergency, you should not appeal to groups, should not shout for someone to help, but should single out an individual, should point to a specific person and say, "You in the red shirt, call 911. And this direct assignment of responsibility overcomes diffusion, makes responsibility clear and concentrated, and significantly increases helping likelihood. And self-defense trainers teach this. Teach that calling for help requires specificity, requires breaking through the bystander effect by eliminating diffusion of responsibility. Another implication is for intervention training, for teaching people to recognize the bystander effect, to understand that their inaction contributes to collective inaction, that everyone assuming someone else will help means no one helps. An awareness of the effect increases helping behaviour, increases intervention rates, and training programs that teach about the bystander effect and provide intervention skills show effectiveness, show that educated bystanders are more likely to help, are better at recognising emergencies, are more willing to take responsibility, and many institutions now provide such training. Colleges offer bystander intervention programs. Workplaces train employees to intervene in harassment or discrimination, and understanding the psychology improves outcomes. The bystander effect also appears beyond emergencies, appears in everyday situations requiring minor helping. Someone drops papers and no one helps pick them up when many people are present. Someone struggles with a door and passers-by ignore them when others are around. And the effect generalizes, shows that diffusion of responsibility and pluralistic ignorance operate in low-stakes situations, not just in dramatic emergencies, and this suggests that the mechanisms are fundamental aspects of social psychology, are default responses to situations with potential helpers, and overcoming them requires conscious effort, requires recognizing the psychological barriers and deliberately choosing to help despite them. Some research questions the original Kitty Genovese narrative, suggests that the number of witnesses was exaggerated, that some witnesses did call police, that the story was sensationalized. And while the specific details are disputed, the bystander effect itself is real, is well documented, is not dependent on that one case, but is demonstrated across hundreds of experiments and real-world observations. And the effect remains one of the most robust findings in social psychology, remains a phenomenon that reliably occurs under controlled conditions. And questioning the Genovese case does not undermine the effect, does not invalidate the psychological mechanisms, but shows that public understanding of the case may be based on incomplete information. The effect also has limits, works differently in different cultures, is stronger in individualist cultures, and weaker in collectivist cultures, where group responsibility is more salient, is stronger in urban environments, and weaker in small communities where people know each other, is weaker when victims are similar to bystanders, when group identity is salient. And these moderators show that the effect is not inevitable, is not universal, but depends on social context, on cultural norms, on relationships. And this suggests intervention strategies, suggests that building community, creating shared identity, emphasizing collective responsibility can reduce the bystander effect, can promote helping even in groups. The woman lies in the street, bleeding, screaming, and windows light up. Faces appear, watch, and no one comes, no one calls. The witnesses assume others will help, assume the situation must not be serious if no one else is acting, and the bystander effect unfolds, responsibility diffuses, pluralistic ignorance emerges, and the woman dies while a crowd watches, and the tragedy reveals something about human psychology, reveals that helping is not automatic, is inhibited by social dynamics, is suppressed when others are present, and the bystander effect remains one of the most important findings in social psychology, remains a demonstration that individual helping decreases when groups are present, that crowds can be obstacles to help rather than sources of help. And understanding the effect is crucial for promoting intervention, for overcoming diffusion of responsibility, for ensuring that witnesses become helpers rather than passive observers. And the effect endures as a permanent warning about the social psychology of helping, about the paradox that more potential helpers often mean less actual help, and the lesson persists that helping requires overcoming social barriers, requires taking personal responsibility, despite the presence of others, requires acting when everyone else is watching and waiting. The consequence argument, why the past makes your future inevitable. A philosopher constructs a deceptively simple argument about free will and determinism, an argument that has become one of the most influential and most discussed arguments in the free will debate. And the argument is called the consequence argument, formulated most clearly by Peter van Inwagen. And the argument aims to show that free will is incompatible with determinism, that if determinism is true, then no one has free will, that our actions are not genuinely up to us but are consequences of the past and the laws of nature, things we cannot control. And the argument proceeds through careful reasoning about what we can and cannot control, about what is and is not up to us, and it concludes that if the past and the laws determine everything, then we determine nothing. We have no control. We are not free. And this is the consequence argument, an argument for incompatibilism, for the view that determinism and free will cannot both be true, and the argument forces compatibilists to explain how we could be free if determinism is true, how our actions could be up to us if they are inevitable consequences of factors beyond our control. And the debate sparked by this argument continues, with philosophers proposing responses, defending premises, clarifying concepts, and the consequence argument remains central to contemporary discussions of free will, a challenge that every theory must address. Imagine the logical structure. Determinism says that the state of the world at any time, plus the laws of nature, entail the state of the world at all future times. Everything that happens is a consequence of what happened before, plus the laws. And now consider your action right now. Reading these words, and if determinism is true, then this action is entailed by the state of the world before you were born, plus the laws of nature, and you have no control over the state of the world before you were born. You did not cause it. You cannot change it. It is a fixed fact about the past, and you have no control over the laws of nature. You did not create them. You cannot alter them. They are what they are, independent of you. And if your action is entailed by things you have no control over, then you have no control over your action. And if you have no control over your action, then you are not free with respect to that action. And this applies to all your actions. All are consequences of the past and the laws, things beyond your control. And so if determinism is true, then you are not free. You have no free will. And this is the consequence argument in its essential form. The argument can be stated more formally using the concept of power, what we have power over, what is up to us. And the argument says that no one has power over the past, no one has power over the laws of nature, no one has power over the fact that the past and the laws entail the present. And therefore, by a transfer principle, if the present is entailed by things we have no power over, then we have no power over the present. And having power over our actions is necessary for free will, and so we lack free will. If determinism is true, and the argument is valid, the conclusion follows from the premises. And so attacking the argument requires attacking one of the premises, requires either denying that we lack power over the past and laws, which seems implausible, or denying the transfer principle, denying that lack of power transfers across entailment. Visualize the causal chain, stretching back into the past, the state of the universe billions of years ago, plus the laws of physics determined the state 1 second later, and that state, plus the laws determined the next state. And the chain continues, moment by moment, through the formation of galaxies and stars and planets, through the evolution of life, through human history, through your birth and upbringing and this present moment. And at no point in this chain did you have control. You were not there at the beginning. You did not set the initial conditions. You did not write the laws, and the entire chain was set in motion before you existed. And your current action is the end of this chain, is the inevitable consequence of factors you did not control. And the consequence argument says, this shows you are not free. Your action was not genuinely up to you, was determined by the past. Compatibilists respond to the consequence argument in various ways. One response denies the transfer principle, argues that lack of power does not transfer across entailment in the way the argument assumes, that you can have power over a fact even if that fact is entailed by other facts you have no power over. And this response requires specifying what power means, what it is to have something be up to you. And compatibilists argue that an action is up to you if it results from your deliberation, your desires, your character, even if those psychological states were themselves determined by the past. And so the transfer principle is false. Power does not transfer, and the consequence argument fails. Another compatibilist response accepts the transfer principle, but denies that we lack power over the past in the relevant sense, argues that we do have a kind of counterfactual power over the past. We have the power such that if we had chosen differently, then the past would have been different. And this counterfactual power is sufficient for freedom, sufficient for the action to be up to us. And critics respond that counterfactual power is not real power, that being such that if you acted differently, the past would have been different is not the same as being able to act differently. And the compatibilist response confuses conditional ability with genuine ability, confuses what would have happened if things were different with what you can make happen. A third compatibilist response distinguishes between freedom and ultimate responsibility, accepts that the consequence argument shows we lack ultimate responsibility, ultimate control, the kind of control that would make us solely and completely responsible for our actions independent of all prior causes, but argues that we have enough control, enough freedom, for moral responsibility, for being proper subjects of praise and blame, and ultimate responsibility is impossible, is not required for the ordinary kind of responsibility that matters for ethics and law. And the consequence argument shows too much, shows that even libertarians who reject determinism cannot have ultimate responsibility because their actions are either caused by prior states or are random, and neither causation nor randomness gives ultimate responsibility. And so, the consequence argument does not distinguish between compatibilism and libertarianism, does not favour incompatibilism over compatibilism. Incompatibilists defend the consequence argument, defend the transfer principle, argue that compatibilist responses involve sophisticated verbal tricks, redefine freedom in ways that evacuate it of meaning, and the consequence argument reveals that if determinism is true, then we are not truly in control, are not genuinely free, and moral responsibility is undermined. And we must either reject determinism or accept that free will is an illusion, and different incompatibilists choose differently. Some become libertarians and argue that determinism is false, that quantum mechanics or agent causation or emergent properties provide room for free will, and others become hard determinists and accept that free will does not exist, that responsibility is problematic, that praise and blame need reinterpretation. The consequence argument also generates discussions about the fixity of the past, about what it means to say we have no power over the past. because in one sense this is obvious. We cannot change what has already happened, cannot make it the case that the past was different. But in another sense, our current actions do affect what the past was, because if we act differently now, then the past must have been different given determinism. And so there is a sense in which our actions constrain the past, and compatibilists exploit this to argue that we do have power over the past in the relevant sense, while incompatibilists insist that this is not real power, not the kind of control required for freedom. The argument stands at the centre of free will debates, forces clarification of concepts, forces philosophers to specify what freedom requires, what control means, what power involves, and whether these are compatible with determinism, and the debate is productive, generates insight, even if it does not generate consensus, and the consequence argument remains one of the most powerful arguments for incompatibilism. One of the most difficult challenges for compatibilists to answer, and Van Inwagen's formulation is elegant, is compelling, captures a deep intuition that if everything we do is the inevitable consequence of factors beyond our control, then we are not truly free and the past stretches back, determined and fixed, and the laws operate, inexorable and unchanging, and the present unfolds and the action occurs, and the consequence argument says, this action was not free, was not genuinely up to the agent, was a consequence of things beyond control, and whether this argument succeeds, whether compatibilists can answer it, remains disputed, remains central to contemporary philosophy of free will. The EPR paradox, when particles know what their partners are doing. Two particles are created together in a quantum process, perhaps two photons emitted from a single atom, or two electrons produced in a pair, and these particles fly apart in opposite directions, travelling far from each other, perhaps to opposite ends of a laboratory, or even to different planets, and quantum mechanics predicts that these particles remain connected, entangled, in a way that defies classical intuition, because measuring a property of one particle instantly affects the other particle, no matter how far apart they are, and the measurement outcomes are correlated in ways that cannot be explained by assuming each particle carried definite properties from the beginning. And this is the EPR paradox, named after Einstein, Podolsky, and Rosen, who presented it in 1935 as an argument that quantum mechanics is incomplete, that there must be hidden variables, additional information not captured by the quantum wave function that determines the outcomes of measurements and explains the correlations without requiring instantaneous action at a distance. Imagine the scenario more concretely. Two particles are entangled such that they have opposite spins. If one is measured to have spin up, then the other will definitely be measured to have spin down, and vice versa. And this correlation is perfect, 100%, whenever both particles are measured along the same axis. And before measurement, quantum mechanics describes each particle as being in a superposition of spin up and spin down, neither definite, and the two particles together are described by an entangled state that cannot be factored into separate descriptions of each particle. The state is inherently joint, and when one particle is measured and found to be spin up, the other particle's state immediately becomes spin down, even if the two particles are light years apart. And this instantaneous correlation troubled Einstein, who called it spooky action at a distance, and argued that it violated the principle of locality, the idea that physical influences cannot travel faster than light, that distant events cannot have immediate effects. Einstein, Podolsky, and Rosen proposed that quantum mechanics is incomplete, that each particle must carry hidden information, hidden variables that determine what the measurement outcomes will be, and these hidden variables are fixed at the moment the particles are created. And so when the particles are measured later, the outcomes are determined by these pre-existing properties, not by any instantaneous influence. And the correlation between the particles is explained by the fact that they started with correlated hidden variables, like two coins that were both set to heads when they left your hand and remain heads as they fly through the air. And when you look at them later, you find them both showing heads. And this correlation does not require any spooky action, just common initial conditions. And EPR argued that quantum mechanics, which does not include these hidden variables, gives an incomplete description of reality. For decades, the EPR argument was a philosophical debate, a question about interpretation and the nature of quantum mechanics. But in 1964, physicist John Bell proved a theorem that transformed the debate into an experimental question. Bell showed that any theory based on local hidden variables, any theory where measurement outcomes are determined by pre-existing properties and where influences travel at or below the speed of light, must satisfy certain mathematical inequalities, now called Bell inequalities, and these inequalities place limits on how strongly the measurement outcomes of two distant particles can be correlated. And Bell showed that quantum mechanics predicts correlations that violate these inequalities, that quantum correlations are stronger than any local hidden variable theory can produce. And so by performing experiments and measuring the correlations, one can test whether nature obeys the Bell inequalities, and if the inequalities are violated, then local hidden variables are ruled out, and quantum mechanics, with its spooky action at a distance, is vindicated. Experiments have been performed many times with increasing sophistication and precision, closing various loopholes, and the results consistently show violations of Bell inequalities, strong correlations that match quantum mechanical predictions, and rule out local hidden variable theories. And so nature does not obey locality in the way Einstein wanted. The particles really are entangled, and measuring one really does instantaneously affect the other. And this is now an established experimental fact, one of the most thoroughly tested predictions in physics, and the EPR paradox has been resolved in favour of quantum mechanics against Einstein's intuitions, though the philosophical implications remain deeply puzzling. The paradox forces a choice between giving up locality or giving up realism, the idea that physical properties have definite values independent of measurement, and most interpretations of quantum mechanics give up realism, accepting that particles do not have definite spin values until measured, that the spin only becomes definite through the act of measurement, and the entanglement means that the two particles are not independent. They form a single quantum system even when separated by vast distances, and measuring one particle provides information about the system as a whole, and this information is reflected in the state of the other particle. But this does not allow faster-than-light communication, because the measurement outcomes are random. Neither particle can control what value it will be measured to have, and so no message can be sent. Only correlations can be observed after the fact by comparing measurement records. Some interpretations of quantum mechanics, like Bohmian mechanics, preserve realism by giving up locality, introducing non-local hidden variables that allow instantaneous influences, pilot waves that guide particles in ways that depend on the entire configuration of the universe. And these theories reproduce the predictions of quantum mechanics and are empirically equivalent, but they are non-local. They violate Einstein's principle that influences cannot propagate faster than light. And most physicists find this cost too high, prefer to accept that realism must be given up, that particles do not have definite properties until measured. Visualize the two entangled particles flying apart, one heading left and one heading right, and they are described by a single wave function, an entangled state that says, if left is up, then right is down, and if left is down, then right is up, but neither is definite until measured. And now imagine measuring the left particle and finding it spin up, and at that instant, even though the right particle is far away, its state changes. It becomes definitely spin down, and if someone measures the right particle immediately after, they will definitely find spin down. And this correlation holds no matter how far apart the particles are, no matter how quickly the measurements are performed, as long as they are performed along the same axis. And this instantaneous correlation cannot be explained by assuming the particles carry definite spins from the beginning. Bell's theorem proves that, and so the correlation is genuinely quantum, genuinely non-local, genuinely spooky. And yet it does not allow signaling, does not allow information to be sent faster than light, because the outcomes are random and cannot be controlled. The EPR paradox stands as one of the deepest puzzles in quantum mechanics, a paradox that led to Bell's theorem, to decades of experimental tests, to the confirmation of quantum non-locality, and to ongoing debates about what quantum mechanics means, about whether reality is fundamentally non-local, about whether measurement is a special process or an ordinary interaction, about whether consciousness plays a role, about whether the universe splits into branches or whether hidden variables exist beyond our current theories, and none of these questions has a settled answer. Different physicists and philosophers hold different views, and the EPR paradox remains a touchstone, a thought experiment that crystallizes the central mysteries of quantum theory. And Einstein's discomfort with spooky action at a distance, his belief that quantum mechanics must be incomplete, has been answered by experiment. Nature really is spooky. Particles really are entangled. Measurements really do have instantaneous non-local effects. And this is not a failure of the theory, but a feature of reality, a feature that defies classical intuition and forces us to accept that the quantum world operates according to rules that seem impossible, that violate locality, that create correlations stronger than any classical mechanism can produce. And the paradox endures, not as an unsolved problem, but as a solved problem with an unsettling answer. And the particles fly apart, entangled forever, connected by invisible quantum threads, and measuring one affects the other instantly, across any distance, and the universe is non-local. And the EPR paradox, intended to show that quantum mechanics is incomplete, instead revealed that nature is stranger than Einstein imagined.